If you are okay, it will be good to let me know, okay, so far I think I'm okay. Let me know. I'd love to hear from you. Should you not be okay, this is when you ask so that we can deal with any question that may arise. Awesome. Beautiful. I'm getting the okays. Lovely. Great. We are all on board. Now, this section is where there's not a lot of questions that will be asked on this topic. The questions that should be asked should have been calculations, but calculations have been removed for some reason that I don't know. But yeah, we'll work with what we have. There used to be 2 levels of calculations here, but they've been removed. So everything that will be tested now is theory. Now, how do we determine the direction of the induced magnetic field and current? Remember, we said when we have a magnet going through a coil, current is induced. Please, I want you to get it. Let me look at it again. I want you to get this point. This is where learners get confused, and I want to really assist you. Number 1 is this. When a magnet moves through a coil, we induce what? Current. Right. Number 2, the current induced. Okay, wait. Don't let me say let me do something. Current is induced in the coil. That's very important. Current is induced in the coil, not in the magnet, in the coil. Now, the current in the coil, we go back to where we started this lesson. The current in the coil has a magnetic field around it. Do you remember where we started from? Around. This was where we're talking about the right-hand rule. Around it. Oh, so I want you to get, it means, check this, we have 2 magnetic fields. I don't know if this statement makes sense. When I say we have 2 magnetic fields, let's make it better. The first magnetic field is the magnet we are using itself. The second magnetic field comes from the wire that carries induced current. Please, I want to hear from you afresh. If what I just said right now is okay, I am noticing the last person that said okay was Oratile before I came to this section. Please talk to me. Is this section okay? Is there a mic on and you want to talk to me? Okay. Please talk to me quickly. What I just explained here, saying when a magnet moves through a coil, we induce current in the coil. Now, the current in the coil will then have a magnetic field. That was the first thing we did in this topic, to prove that when we have a wire that carries current, there is magnetic field. So now we have a coil and there's no current. When we move the magnet through the coil, we create current, and current will have a magnetic field. Hence, we have 2 magnetic fields. 1, the magnetic field of the magnet itself. Number 2, the magnetic field around the wire that carries current. Please talk to me quickly. Is this slide okay with you? Yes, Zainab. A coil is just another word for a solenoid. A solenoid is just multiple coils. So you would see us interchanging the word coil solenoid, coil solenoid. It's just a wire that is wound round. Okay? So, are we okay with what I just explained? I want to take it step by step. Please, is there anyone lost about the two magnetic fields that I spoke about? Okay, Marcia is okay, Zainab okay. Ratile okay, beautiful. Regan, lovely. Afifa, beautiful. I need more, I have more people in class. Because I want to take it step by step. Noela, you okay? Thank you, Umol, you okay, lovely. Ahmad, beautiful. Yes, Amatula. Is the wire that carries the induced current the coil? Yes. So you would see, we would say coil, we would say solenoid, we would say wire, we're referring to the same thing. It's just that a solenoid is now coiled round. Okay, so we're using a wire to create a solenoid, so it's all the same thing. Oh, so we're all good. Beautiful. Now, let's try to get the direction. In getting the direction, there are two things I am going to show you or tell you. Number one, to get the direction, number one, note, to get the direction, we are looking for two directions. Direction of the induced current, we need to get the direction of the induced current, and its magnetic field, Two things we need to consider. Number one, moving a magnet near a coil induces current. Keyword is moving. If it's stationary, it will not generate. So you see, I'm using a coil. We could have it as a solenoid, all right? We could have it as a wire. The three can be used interchangeably. Number two, which is the most important now. The current induced has a magnetic field. I mentioned that earlier on. The current induced has a magnetic field okay? And the induced magnetic field, I'll just say mag field, always, this is where the trick is, tries to keep the flux in the loop constant. By opposing the changed magnetic field. I'll give you a note and I'll spend some good time to explain. But these are the two things that we need to consider. I'll give you a note that you can read, and then I'll spend time explaining. The note is just for reference purpose, so that you can go through again. But I'd love you to listen to the explanation when we say it opposes the change. Okay, so these two things are the things that we are looking at, saying current will be produced, but when current is produced, it induces a magnetic field, and the aim is to keep the flux constant. How does that happen? It will oppose the change. Let me give you an extra note that will assist before I explain. All right. Let's do this. If I have, so that you can see clearly, let's draw a little magnet. Okay? I have a magnet. Let's call this the North Pole and the South Pole. You know that. Just going to draw very few. That's a magnet. That's the first magnetic field that we have. All right? Now we are going to have a coil. And we have a galvanometer, okay, that deflects to show the direction of the coil. Now, let's quickly explain what happens. Now, when we move, okay, let me do this. When the magnet moves towards the coil with its North Pole, the distance between the magnet and the coil decreases. All right, that makes sense to us, because we're now moving towards. All right. Now, when that happens, there will be current induced. Current is induced in the coil. All right. Apart from current being induced in the coil, one other thing that will happen is this. The magnetic flux, let me say full stop there. This is just for reference purpose. The magnetic flux in the solenoid increases. I'll demonstrate. In the solenoid increases. The field of the magnet is towards the right. You would get this just now. The field of the magnet is towards the right. But what is now the implication that we are going to have? We said it's going to keep it constant by opposing. Oh, so now, here is the key. To oppose the increase towards the right, to oppose the increase towards the right, the field produces, or the field rather produced by the current, where? In the solenoid, right? The current is produced in the solenoid, all right, points out of the solenoid, or basically we are saying to the left. That's where we are going. And this we would get according to the right hand rule. So according to the right hand rule, current flows to the right. All right, this is just a lot of notes. Let's go explain. Let's go demonstrate. Let's go demonstrate. I'd like you to just listen carefully because I don't want you to be confused. Now, this is what really happens. The demonstration would make it clear. And then we come back to the note, all right? So don't worry if the note looks a bit gloomy. It's all right. Don't panic. I got you. There are 4 different cases. 4 case scenario that we are going to look at. Scenario. Case 1. Case 1. I think I do have, all right. Let me use this for case 1. Let me duplicate all of this. Okay. Case 1. Let me just use this as case 1. Case 1, I want to use this to explain something to you. Check this. Case 1 is you have a magnet here. Look at where the North Pole is and look at where your coil is. Now we want to determine a whole lot of things here. The direction of the induced current and the direction of what? Current. If this thing is stationary like it is right now, no current is produced. However, I want you to watch this. There is no current produced, but this field, do you see this field? I don't know if that makes sense. The first step makes sense. Remember, that field continues, but there's no movement right now. But that field is just spread out. That field is spread out. It continues everywhere, you know. That one is there. Okay, I'm drawing straight lines. This one continues. That one continues. I hope it makes sense. So there are field lines that would go through the magnet. Oh, makes sense. Parallel. There's no movement yet. Immediately, so case 1 is moving the North Pole towards a coil. Case 1. Moving the North Pole towards the coil. This is the movement now. I'm taking it slowly. That's the movement towards the coil. Check what happens. If we move the magnet towards the coil, I'm going to move this. Okay, wait, before we move, we have a magnetic field, right? We use B to represent that. That's a magnetic what? Field. When we start moving, obviously, okay, let me go back. When we start moving, remember that here we have a lot of magnetic field lines, which tells us it's strong. When we start moving, this distance decreases. Okay? Oh, when this starts moving, it's going to affect what happens here as well. The question is, what will happen at that point? Interesting. There will be what? More magnetic field. Oh. And already that is a change in the magnetic field. Remember, the magnetic field was not so much at first, but once we move, more field lines now go through. Oh, so we create a change in magnetic field. The change would be in this direction. Change in magnetic field. If you get that, we are almost done. So I'm going to repeat. That's the key. First, it was like this. If we then move this towards that, check. You see, there's more. Oops, what happened? Oh, okay. Let me say above. All right, if we move this, just trying to show you the field lines. Do you see it's more? Oh, it's now more. So the change, the more goes towards the left-hand side. Ah, makes sense. So that's my change. But what are we aiming to do? Go back to point number 2. We aim aim to what? Keep the field in the loop constant. So our aim will be now, we have to counter. We have to counter that change. Remember, there's already current produced in the coil. The aim is to counter. To counter that, let me ask you something. My change is towards the left. To counter is going to be similar to friction. Where do you think the direction would be if I want to counter the change? Should it be towards the right or towards the left from your screen right now? We generate more magnetic field here as we move towards. So the change is towards the left-hand side. To counter that change, if my change is towards the left, how do we counter the change? Is it the right or the left? The word counter means to oppose. The word oppose means opposite. Please talk to me and let me know if you're lost. I want to take it. Once you get the first one, the second one becomes easy. I'm gladly waiting for your responses. Current is induced once we start moving. Induced current here. Current is induced. And that current has a magnetic field. So that magnetic field wants to oppose the change that we have created. If the change is towards the right, that magnetic field produced will move to left, right, will move towards the right. This is the induced, let me say, direction of induced magnetic field. The change is towards the left because we are producing more going to the left. Our job will be to oppose that change. So the current produced in the coil has its own magnetic field. We all established that. But that magnetic field wants to oppose this change. So it has to be to the right. I'll get your explanations or questions now. Wait now. Now that we have produced a direction of the induced field to the right, how do we produce current that will now be having the magnetic field pointing to the right? Remember, we have produced current here. We don't know the direction yet. But what we know is the direction of the magnetic field that this current has produced would be to the right. Let's use our right-hand rule. Remember, in a solenoid, it's the opposite, right? The thumb will then be pointing in the direction of the field. Check this diagram. This is wrong. My thumb is pointing towards the left. Wrong. The field is pointing towards the right. So you need to turn your hand around until your thumb points towards the right. Let's see. Okay, looks like we got our thumb pointing to the right. Now look at the direction of current. There. Current now comes this way. Oh, this galvanometer would be pointing that way. Current goes this way. Current goes this way. Beautiful. Now,